it's TMI, but you might hear
It's not
it.
TMI.
Yeah. I didn't eat lunch either,
actually.
so.
Oh yeah,
I'm
that.
starving. I'm so starving. But yeah, do y'all have any questions over the homework?
I had one, I think it was, I don't remember exactly which problem, I think it was the last one on 8.3. It had us do the problem in 2 different ways.
Okay.
And then, got, yeah, I think it's this one. Okay, it might have been 8.2 possibly.
Okay.
But it had us do the problem in 2 different ways, and we got 2 different answers, and it was asking are the answers equivalent, and they didn't look equivalent at all, but somehow they were. Like one of them was multiplied by another factor of x, so I didn't see how you could have but
Okay.
yeah, it might have been this one, I think.
So it was this last part though?
Yeah. I mean, obviously they would be the same, but I couldn't figure out algebraically how to get them to be the same.
So you have so you'd have two different representations as the antiderivative.
Yes.
Algebraic, they probably look a lot different.
Yes.
So I guess for this part C, to verify that they're consistent, you could just take the derivative of both of them
Okay.
to see if they came out to be x over root x plus 15.
Because the antiderivative of b that I got had like another factor of x in it, so I didn't see how they could possibly be the same for another factor of x. And my answer was right, so that was the antiderivative, but I didn't see how to get them to be each other.
Okay. So yeah, I'm not very sure when they say verify that they want you to compare the antiderivatives arts
Yeah.
versus their derivatives being
Yeah, obviously the
integrand.
derivative being the same, but I couldn't figure out how the
So-
antiderivatives really.
Okay. I guess we could work these out.
Yeah.
Do you have
Don't have my work with me.
I have the answer.
expedite that? Was it the same exact one? Just so we can sort of expedite that.
It's actually x plus 25.
X plus 25. I think this was number 11. We'll just change it there. So part A.
It was 2x times the square root of x plus 25 minus 4/3 times x plus 25 to the 3/2
Plus C, okay. That was it. Did I write it down correctly?
Yeah.
Okay, and then for part B,
It was 3/2 times the square root of x plus 25 times x minus 50.
times x minus 50 plus C, so no, is that right? That's about right.
Yeah, it seems about right.
Okay.
Well, it was slightly different because if you multiply that out, you get an x on both sides, and they would differ by a constant. But the way I got it, they would add it together. Having another, not having a factor of x, I think.
Okay. Okay.
Like the one on the top had 2x times that, and the bottom had just a constant times that.
Yeah.
The other side was the same power, if I remember correctly.
Yeah.
So they kind of differ by a constant because there's another factor of x in one of the things that we added together.
Okay, I guess maybe I'll take a look.
Okay.
To be for sure. But to verify that these answers of part A and B are consistent, I guess there's two ways we could verify that. We could try to figure out if algebraically these things are the same. But yeah, I don't know, that kind of troubles me. Verify. So I don't know, I guess verify is up for interpretation. Like what are they wanting? I don't know, I haven't done this problem, I'm not 100% sure. What they want you to use to verify that part A and part B are consistent. But at least initially it would seem like, we're gonna make sure that these two things are the same. Like, is that algebraically equivalent to that, right? The other way is we could just, to me, also verifying would be like, if I'm able to take the the derivative of both of these antiderivatives, I should be able to simplify it to x over the square root of x plus 25. Like, to me, that's verification as well. So without having done this problem, I'm not sure what they want you to do.
If you take the derivative and they're both the same, they can't differ by something other than a constant.
Right.
Okay.
And so when we take the derivative there, remember derivatives could be the same up to a constant. Yeah, I don't know. Did they just want you to select something?
Yeah, it's just a yes or no.
Oh.
Yeah, I put no because they look different, and they're just like, oh, it's yes. It's like, oh, so I get the problem. So again, I put yes for the answer.
Oh yeah. Yeah, I guess. So yeah, I don't know. So is A equal to B? Or is the derivative of A and B I mean, one of those needs to be done. If it's just a yes or no question, probably you just selected yes or no. But in theory, you'd be doing one or the other. So I don't know if that. Let me know if that works. And if it doesn't,
Okay.
we can revisit it.
I mean, I believe that they're the same. It's just the answer. You got to see how you can do the first one. How you can algebraically manipulate things.
Yeah.
So A is equal to B.
Well, I mean, like, I think what we should do here with this one is we should factor out common factor of x to the 1/2 there. And we could have x plus 25 cubed left over. Might be something with this 2x ends up canceling with the 2x over here or something.
And they differ by a constant or something.
Yeah.
Yeah. I can believe that.
So that might be worth trying. I don't know.
Right.
8.2, number 11. I said number 1, it's number 11. Okay, yeah. Any other homework questions?
8.1, number 10. Yeah.
These ones on 8.1 are hard.
Yeah.
You should be really clever to figure out how to do something.
It's not always obvious.
Yeah, that's the one.
Evaluate the following. Okay. Uh, 8.1 number 10. Okay, so I'm just gonna look at this.
It just occurred to me that you could rewrite it.
Yeah.
Use the half.
Yeah, that's like initially what I saw thought of when I saw this. 1 plus cosine 2x. It looks a lot like what we get when we rewrite the integral when we're integrating cosine or sine squared, right? But that's reminding us of this identity. Right? And that should be somewhat familiar because we've had to integrate sine, cosine squared kind of frequently. So that's, the thing I'm trying to integrate under the radical is actually just 2 cosine squared. So that helps out a lot. Between 0 and pi over 2, can we ensure anything about, what can we say about cosine when x is in between 0 and pi over 2? Cosine's positive, right? So we're not going to worry about the square root of cosine squared is the absolute value of cosine. Technically it is. We don't need the absolute value because from 0 to pi over 2, we know cosine's always positive. So this just turns into constant root 2 times cosine.
Yeah, I can handle it from there.
Alright. Yeah. So then we'll, we'll again mention that it's since x is in the interval from 0 to pi over 2, pi over 2, cosine's positive. That way we don't have to worry about this right here. Does that make sense?
Do we have to write like the x, like inside like the 0 to pi over 2? We have to write that one.
You don't have to write that. Like, I think it's helpful because sometimes I think we're just used to taking the square root of something squared and just saying it's that quantity, but it's really the absolute value. I don't know that I would expect you to write that out. I would just maybe assume that you knew that, or would hope when I'm grading your exam that was the case.
Yeah.
If
That's
you
why
did
I
write
asked
it
like,
out.
that's why I just asked like, on the exam do we have to write it down or not?
Yeah, I don't think so.
Okay.
I think it's fine. Because we see a lot of this kind of stuff in 8.5 when we do trig substitutions, sorry, 8.4 when we do trig substitutions, and those problems are set up to where we don't have to worry about integrating an absolute value of a trig function. It's always just the square root of something square is the quantity, but those problems are set up to be that way. Okay, so yeah, any other questions about this or other homework questions? So in 8.4, the method of integration is using trigonometric substitutions. It means we're going to substitute a trig function in for an expression for x. So instead of letting u equal a function of x, we're going to let like sine theta equal a function of x. And before we do that, sort of some preliminary stuff here, this basic stuff that we, most of it we will need in this section to do this. So we have, however you call these things, we're going to call this the opposite side, the hypotenuse, and the adjacent. I think that's pretty standard. We do have to remember this stuff. You will end up, when you make a trig substitution, you will end up drawing a right triangle so you can substitute back in for your original variable. So the sine was the opposite side over the hypotenuse. The cosecant then is the reciprocal of that. Cosine was the adjacent side over the hypotenuse. So secant is hypotenuse over adjacent. And tangent was opposite over adjacent, which means cotangent was adjacent over opposite. So just have that there as a reminder. You will have to utilize this. Okay. Another thing we have to utilize is here in example 1. So given that the sine of theta is x over 8, what we want to do is draw a right triangle to determine the value of cosine. Assume theta is in between 0 and pi over 2. So that's kind of where all this stuff comes in. We're this angle here, theta. And we know the sine of that angle is x over 8, which means that's the opposite side over the hypotenuse. And in order to find cosine then, of course, we need the adjacent side over the hypotenuse. So we need to know what is this side right here. What is the length of that side of that triangle? We just use the old Pythagorean theorem, right? Hypotenuse squared is this side squared plus this side squared. Here's our unknown. So that's that length of that triangle side. So, you know, in fact, we could not only just find cosine, now that we have this reference triangle, we could find sine, tangent, cosecant, secant, find everything, but we're asked to find cosine theta. Cosine of theta is this side over the hypotenuse. Does that make sense? Does anyone have questions on that? So these kinds of triangles that we just did here in example 1, that's exactly how we go from our substitution back to the original variable. So like, you know, this kind of situation with our right triangle and theta, that's kind of like our u. But every time we find the antiderivative of u, we then resubstitute x. So that's kind of like the u situation over here, and this is figuring out what that is in terms of x. So that's utilized with every trig substitution. Okay. Does anyone have questions? So I guess we're gonna just motivate this or illustrate this with one particular example. But you know, initially you might think like, why do I want to sub a trig function in for a function of x? Generally that makes it a little bit more complicated. So why trig sub? Yeah, so we'll just consider the square root of 1 minus x squared. In the back of your mind, think about being able to find the antiderivative of this. So could we find the antiderivative of the square root of 1 minus x squared? Can't do it by parts. We can't use u substitution because the derivative is negative 2x. You don't have another x hanging out. That's it, right? So when we see how to like substitute, like always keep in mind the Pythagorean theorems for the trig functions, like 1 minus or sine squared plus cosine squared equals 1, which means 1 minus sine squared is cosine squared, right? So like to help remember how to set these up or which substitution you make, you want to remember the Pythagorean theorems for trig functions. So if I say, well, I don't really know what this is, I can't simplify it any further, but if I said let's let x equal to the sine of theta. Again, why would we do that? Because now we can write this as the square root of 1 minus sine squared. And what do we know equivalent, what is equivalent to 1 minus sine squared? It's cosine squared, right? Now we've turned a sum, or in this case, we've turned a difference, sorry, that's theta. We've turned a difference of squares into a single square. So now you can take the square root of that. So, I mean, in short, that's why we want to use trig substitution. There's some stipulations we're making about where theta is to say that the square root of cosine squared is cosine, but about absolute value. So, like, I couldn't find the antiderivative of the square root of 1 minus x squared. Making a trig substitution gives me a little bit more hope. There's a little bit more to it than that, but that's the basic idea. That's why trig substitution is hopeful in a lot of instances. Okay. Any questions or comments about that? Does that make sense? So if you're looking through your textbook, for the trig subs, they have just a slightly different method where they sort of like factor stuff out after the fact. So they make a substitution first and then they factor stuff out. The way we're going to do it in class is we're going to factor out first and then make a substitution. So it's 6 in one, half a dozen in the other. If you prefer the books method, then feel free to do that. So like when we see 16 minus x squared, the way we're going to handle this in class anyways is we're going to factor out a 16 from both terms. So we factored a 16 out. And then we can take the square root of 16. So we're going to just take the square root of 16 out. And then we have the square root of 1 minus x squared over 16, and we're just going to write that x squared over 16 as x over 4, quantity squared. Your textbook has just a slightly different approach, but either way you go about it, you're going to have to factor stuff out. And so at this point, like if, again, we're pretending this is going to be a part of an integral. At this point, we would then say, well, I've got 1 minus x over 4 squared. In this instance, I want x over 4 to be my sine of theta. I'm thinking about the Pythagorean identities. 1 minus sine squared or 1 minus cosine squared. So I could let x over 4 be cosine as well. And again, that's just 4 times the square root of 1 minus sine squared. Which is just 4 cosine theta. So similar to the example above, but just slightly more involved because it's not a 1 minus x squared. But that's kind of the idea. Does anyone have any questions? So our 3 cases, the three instances that we see with trig substitution primarily here, a squared minus x squared, a squared plus x squared, and x squared minus d squared. So like I said, how we're going to look at it is different from how the textbook looks at it. So down here, with the steps, those are just from your textbook. Our steps are going to be slightly different because the textbook says choose the correct substitution, where it's a sine theta, a tangent theta, or a secant theta. Ours will be a little bit different because we're simplifying the sums with difference of squares first. So from this one here, a squared minus x squared, we're going to rewrite it like we did, where we factor out the a squared. Yeah, we'll just write it like this. Sorry. We'll write it like this first. So we just factor out that a squared, and then we write this as this here. And really it's the the 1 minus the quantity squared. It's going to be the 1 plus the square or the squared minus 1 that dictates what our substitution should be. So always in the back of our mind, we're going to think about the Pythagorean identities. 1 minus a sine squared, like we saw in the last 2 examples. So if you've got a situation like this, your substitution should be x over a equals to sine of theta. And if that's our substitution, then what that gives us is this reference triangle where this, if this is theta, then this side has to be x, this side is a. Like, and this side here, solve for it, that's a squared minus x squared. So I don't really think that you have to remember a whole heck of a lot of information. Like I said, the sum or the difference of squares portion tells you what substitution you should make based off the Pythagorean identities. So like a squared plus x squared, we factor the a squared out again, we have 1 plus x over a, quantity squared. That tells us our substitution should be x over a equals to, what would we sub there? Tangent, right? Because 1 plus tangent squared is secant squared. It's another square itself. 1 plus tangent squared. Is everybody okay with that? I'm looking right here to base my substitution. Theta, tangent, is this here? Hypotenuse then would be square root of a squared plus a squared. And then finally here for x squared minus a squared, we're still factoring out the constant. We're factoring out a squared. And then we'll have this time x over a quantity squared minus 1. So what Pythagorean identity is something squared minus 1 equaling another square? Secant, right? Secant squared minus 1 is tangent squared. If for instance we let x over a be sine, then you've got a sine squared minus 1. That's not a square. It's not cosine squared. So secant squared minus 1. Therefore this x over a should be secant. Is everybody all right with that? Does it make any sense? Questions? Jason, so that's, what am I doing? Oh, I'm labeling this here. All right, so again, any point in time you make a strict substitution, in order to shift it back to the original variable, you're gonna have to think about one of these right triangles depending on what substitution you
And
made.
then you have to switch like the x is on either side. Okay.
Which one?
Like the third one.
The third one?
Yeah.
So it is something you refer to every time you make a trig substitution. Hopefully you're writing it down so you're not mixing stuff up. Maybe in your head, I don't know. But these steps that are listed below come from the textbook. And we're just gonna, oops, typo there, 8.2. Wait, integrate use techniques from 8.2 and 8.3 lot of those integrals from 8.3 show up as well, like antiderivative of tangent, whatever. So the only difference we're making is pretty much in step 2 in how we choose to identify the substitution, and this what we have up here is how we're doing. So step 2. Okay, so let's look at something like this. Now, I think it is worth mentioning, like if this were a definite integral that you had to evaluate, sometimes you can figure it out like using geometry, sometimes not so much. But something like this, you could look at a calculus 1 type of approach to evaluate that definite integral when you recognize what kind of function we're dealing with here and what the bounds tell us. So like if it were a definite integral, you really wouldn't need any calculus to evaluate that. Because what is the graph of square root of 64 minus x squared look like?
A circle centered at the origin with a radius of 8.
Circle centered at the origin with a radius of 8.
The first quadrant in this case.
Right, because this is what we have boxed as y. Square both sides, we have y squared equals to 64 minus x squared. Put x and y squared on the same side. So it's saying from 0 to pi over 2. So all it's asking for is the area of a quarter of a circle. We could totally find that without calculus. Quite a different story when we're asked to just find the antiderivative though. So this is where we're going to use trig substitution. We've got difference of squares, and we're taking the square root of that. So can I turn that into just a square? So I can take the square root of that square and it goes away. Yeah, with trig substitution. So we're going to, again, kind of just factor this 64 out. We've got our 1 minus x squared over 64, all under the radical. We're going to take the square root of 64, put it out front as our constant. And then we're going to rewrite the x squared over 64 as a quantity x over 8 squared. So once you do a couple of these, this step is pretty much automatic. Of dx. All right. So what's our substitution here?
X over 8 is equal to sine theta.
X over 8 equals to sine theta. Do you all agree? 1 minus sine squared will give us a complete square. Yeah.
Why are we using sine instead of cosine?
It's arbitrary. You could use
Okay.
cosine if you
They-
wanted to.
they both work, okay.
Yeah, they both work, for sure.
Just not with the secant and tangent method because they're not interchangeable.
Right, right, yeah. You could make a trig substitution with the a squared minus x squared as cosine instead of sine. Works out the same. Yeah.
Do you ever do that with the bound change?
No. No, so when we look at a definite integral in this situation, what I would recommend first is just finding the antiderivative first and then plugging in the bounds.
Gotcha.
Because if we had bounds from like 0 to 5, and then we would just have to figure out, okay, well x is 0, then the sine of what gives me 0, put that up there, it's just a little bit more involved, I guess.
Makes sense.
Okay, so what we didn't do when we made our algebraic procedure in the first page, we didn't account for this dx. So just like with any other substitution, you have to take the derivative of your substitution. So we want to account for that dx. The only way to do that is to take the derivative. So we're kind of looking at this like x is 8 sine theta. So when we take the derivative of x with respect to theta, we have dx equals to 8 cosine theta d theta. And then we're substituting in for what we have. We have our 8, the antiderivative here. That was sine. And then our dx was another 8 cosine theta d theta. All right, so now, it's a crucial step. The d thetas, the dx's, we saw that come up with integration by parts. We're seeing it come up again here. I just ask that you try to be as diligent as possible with putting those d thetas, the dv's, the dt's, whatever. Okay, so we have our 8 times 8. We'll go ahead and put our constants here. This is now cosine squared. 1 minus sine squared is now cosine squared. And then we still have that times this cosine. Does anybody have any questions on where we're at? Okay, so the square root of cosine squared is cosine times the other cosine. We've got 64 times the antiderivative of cosine squared. Theta with respect to theta. Yeah. There's cosine squared again. How do we integrate that? Remember you either remember it by now or you remember the identity. So we're going to rewrite this as, I'm going to go over here, save some space. We're going to rewrite cosine theta 1/2 theta plus cosine 2 theta. Antiderivative of theta. Sorry, that's 1. I got ahead of myself. That's 1 plus cosine 2 theta. My bad. 1 plus cosine 2 theta. 64 times 1/2. Antiderivative now. Antiderivative of cosine 2 theta is what? Half sine 2 theta. And then we have, we'll just put our constant out here. Okay. Questions at this point? So we've substituted, simplified, integrated. Now we have this expression involving theta. We want this expression to involve x. So now we have to convert all this theta stuff back into x's. And that's where the triangle comes in. So we're going to use this triangle to change our thetas into x's. So again, in order to do that, we have to go back to our substitution. Our substitution was sine of theta is x over 8. So here's the sine of theta is x over 8. Does that make make sense? Okay. This side, Pythagorean theorem again, 64 minus x squared. Just go ahead and find that third side. More often than not, you need it. Okay. So that gives us sine, cosine, secant, cosecant, cotangent, tangent of theta in terms of x. However, we have a theta here. What is theta in terms of x? Right.
Side of like x over 8.
Right. So that again goes, we don't have what theta is here with this picture, but we do have it from our substitution, right? If x over 8 is sine theta, then what is theta? It's just the inverse of that side. Inverse sine of x over 8 is what theta is. Yeah?
Well, so I'll just put it here. The inverse sine is theta.
So, okay, great. We've got a way to account for this theta, but also a problem here with the sine of 2 theta because we just have a theta here. We don't have a representation for 2 theta.
The sine 2 theta is the 2 times of the sine theta times cos theta.
Yeah, so that's what we're going to use. We're going to use that identity for sine 2 theta at this, for this one here. Oops. Sine of 2 theta is 2 sine cosine. And then that way our arguments are thetas and we can reference this triangle. So sometimes you need a little bit more work before you just jump into that triangle there. So we have 32 times our theta, is it plus, and then we've got a 2 sine theta turning into 2, or sine 2 theta rather, turning into 2 sine cosine. That'll divide that 1/2 right there. So we just have this sine cosine. Then we have plus c. All right, we've already talked about theta. Itself is inverse sine of x over 8. We have that there. Plus sine theta times cosine theta. We're using this triangle here. Sine theta was x over 8. And cosine theta is
The square root of 64 minus x squared over 8.
right. Cosine is the adjacent side over the hypotenuse, the square root over 8.
I guess I should have done that right, but whatever.
So that's pretty much it. Anyone have questions about that? I don't know that any of them get any simpler. It's kind of par for the course with trig subs.
Cody, real quick.
Yeah.
How'd you get sine 2 theta equals 2 sine theta cosine theta?
That's just the angle, or the double angle identity for that.
Oh, that's just a trig identity.
Yeah,
Okay.
right. Right. That one's really common. So put that in your head. It does come up quite frequently.
What's the cosine 2 theta one again?
What's the cosine 2 theta? There's 3 of them, right? There's 3 ways to represent cosine 2 theta, all based upon cosine squared minus sine squared. we just write one or the other with its Pythagorean combined like term. So you get 2 cosine squared minus 1 as the other one, and then 1 minus 2 sine squared as the third. Yeah. For sure, sine 2 theta is a lot more common than cosine 2 theta. I don't know why. Maybe it was just the textbook and the author problems they chose, but that's really common. Any other questions on any of that? Okay. And we'll just clean this up a little bit. 32 inverse sine. X over 8. 64, 32 over 64, 1/2, so we have this. So again, the derivative of all of this stuff should be the square root of 64 minus x squared, once you simplify that.
So I have questions. So if I call like x over 8 by cosines, and that should be different answer.
Yes, right. So if we let our substitution x over 8 be cosine, you'd have something slightly different than what we have here. You see that? So if we have this, same identity still works. We still have to find dx. dx is now different. We have 8 minus 8 rather sine theta d theta, the derivative of 8 cosine. So this thing comes. What do we have? We took a 64 out from the square root. Then we have that. And we have this. Our d theta minus 8 here. So the difference, if we let our substitution be cosine instead of sine, is now this turns into sine squared, the square root of sine squared is sine, times this sine. We have to integrate this with respect to theta and our constant out here. So you end up with a bit of a different answer, right? The identity for this one is now 1 minus cosine 2 theta. So you got that minus there that you didn't have. So the negative 64 out here is multiplied here. So that's going to be a negative 32. This is going to still be a positive like we have over here. So you can totally go through that and verify the antiderivatives are, in fact, once you simplify them, the square root of 64 minus x squared. I'm not sure why conventionally it's chosen as sine instead of cosine, because they both work. It's not that, like, if I let my substitution be sine instead of cosine, that I'll always get an easier integral. They're always, like, super comparable. Yeah. Any other questions? Okay, next example. Antiderivative of 1 over root 36 minus x squared. Does anything jump out at you? So we'll go with this. Difference of squares here. I'm gonna, under the radical, factoring the 36 from 36 minus x squared. So I have 1 minus x squared over 36 times 36. Which we're gonna work with as, we're careful this time though, we're taking out the square root of 1 over 36. So you're taking out a 1 over 6. Over the square root of 1 minus the quantity x over 6 squared. So our substitution should be what? Sine again, yeah. It's 1 minus a square. We want x over 6 to be sine theta. So then what is dx?
6 cosine.
6 cos theta?
Yep.
6 cosine theta d theta differentials.
Okay, then we resubstitute. We have our 1/6 antiderivative. Dx is now 6 cosine theta d theta. And we've got the square root of 1 minus, excuse me, 1 minus sine squared. So the 6th and the 1/6, those are gone. We have the antiderivative of cosine theta over the square root of cosine squared. So we have cosine over cosine. What's the antiderivative of d theta? Or sorry, the antiderivative of 1 with respect to theta is theta. Constant. What's theta?
Inverse sine x over 6.
Yeah, if, again, sine theta is x over 6, so theta is inverse sine of x over 6 plus c. Now we recognize that integrand was totally in that form, right? Remember, inverse sine is one you should definitely know. Theta is inverse sine of x over 6. So great, if you don't remember that that's inverse sine, now you have trig substitution. We'll tell you that it is inverse sine. But definitely worth remembering that. 1 over the square root of a squared minus x squared is the inverse, the antiderivative is the inverse sine of x over a. So we could have just wrote that down immediately, not needing trig substitution. But trig substitution works, so either way. The other one we should remember was this one. One over a squared plus x squared, what is that? Inverse tangent is involved, yeah. Inverse tangent of
1 over a in the beginning.
1 over a, close.
X is
Yeah, x over a, or x times 1 over a.
I'll say in the beginning.
Oh, in the beginning, right, yeah, and also don't forget the constant, 1 over a. So the inverse sine and the inverse cosine were the only ones that didn't have that extra factor of 1 over a multiplying them. The other inverse trig functions do. So don't forget that. If you forgot it, either one can be figured out with trig substitution. But why do trig substitution if you don't have to?
Because it's fun.
Is that you being facetious?
Maybe a little bit.
Maybe a little bit. I don't know. It's pretty cool, but I don't know that it's fun.
Yeah, it's cool.
It is cool.
You got me on that one.
I'm just curious, this is kind of a tangent. So the one on the left, you take the integral of that, we get the one on the right. How would you go about taking the derivative of the one on the right to get the one on the left?
For this one?
Yeah, just in general, how would you take the derivative of that?
Take the derivative of.
Like without relying on some sort of integral identity, just like analytically determining what the derivative of inverse tangent is.
Oh, I see. How do we know what the derivative of inverse tangent is?
Yeah.
It's
how would
basically
you-
your question, right?
Yeah, that's why I said it's a tangent, because it's not really related to this. And I thought it was
Yeah, certainly. So like, let's just, like, if you're just posed with that problem and you wanna know how you take the derivative of that, the way it's typically shown is we don't think of it like this, but we think of it like this. Okay, and then we use implicit differentiation. So we're thinking of y as a function of x. So what's the derivative of tangent? Secant squared. So we multiply by y prime. Derivative of x is 1. Solve for y prime. Y prime is 1 over secant squared. Y. And then we need y in terms of, or we need secant y in terms of x if we're going to say the antiderivative, or the derivative of inverse tangent is 1 over x squared plus a squared, or a squared plus x squared. So this is where our Pythagorean identities come in. Like we say secant squared of y is 1 plus tangent squared y. So we have then our y prime is 1 over 1 plus tangent squared y. And what's tangent squared of y? Tangent squared of y is x. So that's x squared. So there we have our derivative for inverse tangent. And the other trig function, inverse trig functions are configured the same way.
Okay.
Implicit differentiation. They do have restrictions when we rewrite. So like inverse secant and inverse cosecant, they have restrictions on their.
Yeah, there'd be a domain issue doing that.
Yeah.
But
So you actually have two derivatives for those, which are put together as one with the absolute value plus and minus. Okay. All right. Any other questions? All right. Let's take a break.
put my name or just like a check mark?
Yeah. Put your name. No one's gonna hold you to it again. It's just a straw poll.
I'll look to mine.
For those of you at home listening, if you're interested in differential equations in fall of 2020, please email me. I don't know how many people actually watch these. You do? I've never watched one. I hate my voice, so I don't want to subject myself to that torture. All right, back to trig substitution. So like this is an example of another instance where it would work. And you know, the first two did have square roots. We're returning sums and differences of squares into a square itself. But also in a situation like this, it could prove useful. We still do have like a square plus another square being squared. So let's see how this unfolds in a situation like this. In the next section, 8.5, we will look at like when we have like polynomials divided by other polynomials, like rational functions, how we can integrate those. With something like this though, trig substitution would still be the easier approach. So again, when we look at this, we think, all right, well, does a u substitution work? No, my derivative would involve a 2x. I don't have an x on top. So that's really the main indicator that a u substitution wouldn't work. We could write this as 18 times 81x squared plus 1 to the negative 2, but that's not really giving us a product. We could try integration by parts in the sense that we tried integration by parts with that integral, and where we let dv equal to just the dx part. So that we could try that. But really it's the square plus the square and whatever else we're doing to that, that sort of leads us to believe that this is probably a trig substitution. So we're gonna just reorder some things. We're gonna factor the 81 out. Of our square plus 1. Well, I guess we could do that. I don't know if we want to do that. Do we want to? So the goal here really is to turn this 81x squared plus 1 into a trig function that's being squared. So we want to turn those two terms into a single term. So let's see what happens. Oops. Not that. Okay. And so we'll take that 81 out, whatever this reduces to, if it reduces. Let's just see how this looks after we're done with this. So that's, you know, we could probably proceed this way, but the issue is now we're thinking, all right, well, what square plus 1 over 81? It kind of like falls. So the other ones we had, you know, a square minus 1 or plus 1. We had our trig substitute, our trig Pythagorean identities applying directly to those. Okay, so it's probably not the best route to factor this 81 out, like we've done with the square roots and stuff. Okay, so let's reformulate that. I mean, we could do that. There's nothing wrong with it. It just doesn't seem like it's going to be helpful. Okay, so we have our 81x squared plus 1 squared. All right, what should we do from here then?
You can take a 81x squared and turn it into parentheses 9x squared, and then let that equal to tangent of theta.
Okay, that's exactly what we're gonna do. So we're gonna rewrite this, or look at 81x squared as 9x quantity squared plus 1. And all that's squared. So there's our 81x squared plus 1 squared. Okay, now we have a square plus 1, and so we're thinking now what trig identity? Tangent squared plus 1 is secant squared. So our substitution, we're going to let 9x be tangent of theta. And so dx would be 1/9 secant squared theta d theta. Because x is tangent over 9. Okay. So at least that configuration's a little bit better because we can now use a trig substitution. The other one with the 1 over 81 is kind of weird. So we have our 18 antiderivative, our dx, 1 over 9 secant squared theta, d theta, and then our quantity squared on bottom is just tangent squared plus 1.
constant is now 2. We have our secant squared theta d theta over tangent squared plus 1, secant squared, and that's being squared. So we're integrand secant squared over secant to the 4th, or 1 over secant squared. All right. Is that okay? Does anyone have questions on what we've done? How do we find the antiderivative of 1 over secant squared? Yeah, you just call it cosine squared. And there we are back at integrating cosine squared. So the identity, the 1/2, is going to cancel with the 2. It's going to turn into the antiderivative of 1 plus cosine 2 theta d theta. Okay, so we get theta plus our sine 2 theta over 2 plus our constant. And again, we see that sine 2 theta, we don't want that. We want our triangle is in terms of theta, so we want everything in terms of 1 theta. So we're going to rewrite sine of 2 theta as 2 sine theta cosine theta. Divide those 2's out. Are there any questions? Then once we have this, we've got to turn this back into a expression involving x. So that's where we use our triangle. Okay, I'm just going to rewrite. Our original substitution was we let 9x be tangent. So we're just thinking of that as 9x over 1. Okay. Our hypotenuse would be
Square root of e1x squared plus 1.
so this thing hypotenuse
The square root of x squared
plus
plus
1. Okay. So that'll help us account for this sine and this cosine. What's theta?
the inverse 10 9x.
Yes. From our substitution, tangent theta is 9x. So the inverse tangent of 9x is what theta is. Okay. So tangent inverse 9x is theta plus sine of theta 9x over the square root of 81x squared plus 1. Sine theta times cosine theta. Over the square root of 81x squared plus 1 cosine theta. And we'll just clean that up a bit, but that's pretty much it. Anybody have any questions at all? Okay, so we've got our inverse tangent 9x. Plus 9x over 81x squared plus 1 plus. Questions? So as far as definite integrals go, usually with the u substitution, your u substitution as a function of x isn't too complicated. So I guess it's a matter of preference. I usually don't convert my bounds or convert back to x and then plug in the bounds. I usually convert the bounds in terms of u. For these, I don't know, I tend to lean towards finding the antiderivative first, putting it back in terms of x, and then just evaluating it from 0 to 1 in this case. But if you want to convert into thetas, feel free to do that. So we're just going to work on this piece first, and then address the bounds once we find the antiderivative. So this is another square root of a sum of squares. And we're going to factor out the 16, do all that stuff, the algebraic stuff. We have the square root of x over 4 quantity squared plus 1. And we factored out a 16. We took the square root of 16. It's on the bottom, so we have our 1 over 4 here. So algebra. Similar to that last problem, we have a square plus 1, so we're gonna let our square be tangent. Take the derivative of that. And then plug in our substitution. So we have 1/4 antiderivative dx 4 secant squared theta d theta over the square root of tangent squared plus 1. Our constants go away. Our integrand simplifies to what? Just secant, right? We've got secant squared over the square root of secant squared, which is secant. So we've got secant squared over secant. antiderivative then of secant?
No, maybe it's the second term.
Okay. Yeah, that was one of those funky ones that we addressed in 8.3. We have to know that. Because you get to this point, no reduction formula, integration by parts, anything else is going to help. Or you remember the procedure. Oh, I multiplied that by 1 in the form of secant plus tangent over secant plus tangent. Then it was a U substitution, et cetera, et cetera. ln absolute value of secant plus tangent. Plus constant. Okay. Antiderivative in terms of theta. Now we're going to draw the triangle to convert back to x. What was it? 4. I think of our substitution, x over 4 was tangent. Let me just double check. Yeah. X over 4 was tangent, so we have this side. This side. Opposite over adjacent. This side. It's the x square root of 16 plus x squared. Okay, so now we know secant is what?
Square over 4.
Okay. Square root of x squared plus 16 over 4 plus tangent.
X.
Yeah, we know that one was our substitution. That's x over 4. Let's see. So there's our antiderivative in terms of x. We can actually simplify this a little bit more, but does anyone have any questions on where we're at this point? Okay. So that we could just throw this in, evaluate it from 0 to 1. The other thing that's kind of common that you might see if you're looking through your text, or maybe if you're like, help me solve this with MyMathLab, they might do this as well. But we do have the logarithm of the square root of x squared plus 16 plus x all over 4 plus c. And now we have the log of a quotient. So we can view that as the properties of logarithms. That's the log of the numerator. Minus the log of the denominator. Again, this step from this point here, from that point there, what we're doing after is not totally necessary. And what happens with the minus ln of 4? Well, that's just another constant, right? So we absorb that constant in with our plus c, and we just have some other constant. We know when we do definite integrals that the constants don't matter because they end up subtracting out. So we could simplify this a little bit more and just say that's the natural log of this thing plus x plus some other constant. We'll just call it constant 1. But this right here is a constant. So you've got a little bit simpler of an antiderivative to work with. Okay. Again, not absolutely necessary that we do that. One way or the other, take one of those antiderivatives because we have to go back up and evaluate the definite integral. No. we've come up with that antiderivative is this thing. And we can also make this a little bit easier too if we wanted to from this point. We're evaluating from 0 to 1, x is in the interval from 0 to 1. Do we really need the absolute value there? The only reason we have the absolute value is to ensure that we're not taking the log of a negative number. If x is in the interval from 0 to 1, then the square root, of course, is always positive regardless of what x is, plus 0 or anything up to 1, right? We have a positive quantity. Technically, you don't need the absolute value here in this case. You know, if it's ambiguous or confusing to you, then just keep them. But we're going to work with this. There's no harm in keeping them when you shouldn't keep them. So we're going to just look at this. And evaluate that. Plugging in 1, we have the natural log of the square root of 17 plus 1. Minus the natural log of the square root of 16 plus 0. So I guess we'll just leave this exact. It's usually preferred to leave as an exact. So that's our exact answer. Again, the other thing we could do, we've got the log of this minus the log of that. We could write that as a single logarithm using properties of logarithms, but I don't know that that's absolutely necessary either. Which is maybe a little cleaner, I don't know. But if the thing that we starred, if you were to work with that, you would get the same exact answer. Any questions on that? This example and the next one are sort of similar, so why don't we forego this example? We've got to start 8.5 today. We'll forego this example. The answer is, just put the answer here just in case you want to work this. Natural log absolute value of x over 9 plus the square root of x squared minus 81 all over 9 plus some constant. So we see that thing again. What must have we ended up integrating to get here? Yeah, secant. That's the natural log of secant plus tangent. Or doing the same sort of algebraic trick, we can say that's the natural log absolute value of x plus the square root of x squared minus 81. Where the natural log of minus the natural log of 9 gets absorbed with this constant here. So I don't know, I'll just kind of be sloppy, but either way, one or the other is what you should get. So why don't y'all start working on this? The stipulation here that y is larger than 9 is there, so we don't have to take, when we take the square root of something squared, we don't have to call it the absolute value. We can just
say that it's that quantity. So I'm gonna try to find that from your textbook while you get started on this. Put it in our notes. Right here.
So yeah, as we saw, all of the y's need to be accounted for in terms of theta. So that's where you end up. I want to just pause there for a moment. So it's sort of technical. What's mentioned in your textbook, though, however, in this table 8.4, it says if the integral contains this expression, then a good substitution is this, and then it has all these restrictions here, here, and here for where x needs to be. So those are basically when we make the substitution, if x over a is sine, then we know the inverse sine of x over a is theta. So the inverse sine has specific things that you can plug into it, from -1 to 1, and the inverse sine outputs specific things from -pi over 2 to pi over 2. So just think about these thetas as like the input for like the inverse sine, or sorry, for the sine rather, but it's based on the fact that x over a in this situation right here would be, the inverse sine of x over a is theta. Does that make sense? If the inverse sine of x over a is theta, then the output for that is only between -pi over 2 and pi over 2, because that's the range of the inverse sine. But anyways, these things are mentioned here kind of in passing, and then they say, in order for the tangent substitution to be positive, blah, blah, blah. So that's where they go through all of that. For us, what it boils down to really is we don't have to worry about it, because in certain instances that normally we would worry about it, like in this one, the y greater than 9 here is allowing us to bypass the positive and the negative when we take the square root and just look at the positive. Okay. So that's in your textbook if you wanted a more like in-depth reason as to why we're not looking at that. And again, how that plays out is our square root secant squared minus 1, so we're going to have the square root of tangent squared, and we don't need to worry about that being the absolute value of tangent. We're just going to call it tangent. Okay, so this 9 and this 9 is gone. We still have this 9 out here. We have the integral of square root tangent theta squared. The secant is gone. So I guess we don't have anything up there. Get rid of that. Tangent theta d theta. And then that gives us 9 antiderivative of tangent squared. So like even like an integral like tangent squared, after we've seen all of these powers of trig functions, reduction, identities, so forth, sometimes little things like that can trip us up. But integrate tangent squared, you're just going to rewrite it as secant squared minus 1 using the Pythagorean identity. And I guess you could use a reduction formula, but those aren't required, so we don't know those. So we're going to rewrite tangent squared like that. Antiderivative then of secant squared is just tangent minus this theta, antiderivative of 1. We have our constant. So that's what we had. Turn this back into x. Y over 9 is secant theta. Is our substitution. Okay. Anybody have any questions?
Can you go like one step here? Can you explain me the step after the 9 times 20 times?
So to go from here to here, yeah. So we just rewrote tangent squared because 1 plus tangent squared is secant squared with Pythagorean identity. So we just solved for tangent squared and wrote it as secant squared, because we can take the antiderivative of that easily. Are there any other questions? Okay, so we have 9 times the tangent of theta. There's the tangent of theta minus theta. Theta now is the inverse secant of y over 9. That's pretty much it. Okay. So something like this, we'll see more of these types of problems in 8.5. Really the problem with something like this, even in methods from 8.5, don't really help us with something like that. We'll sort of see why once we get in the next section. So what we're gonna do first is complete the square on the bottom. So half of 2 added, we have x plus 1 squared. And we subtract 1 from 37, so plus 36. Jump over here. So maybe, if you don't remember that, gotta refresh. Sometimes completing the square does come up. You probably saw that in 8.1 as well. Okay, so we complete the square on the bottom. Now we have a square plus another square. dx. And so at this point, there's a couple of options, I guess. Anybody have suggestions for what we should do with that?
So we call x plus 1 equal like sec 10.
Okay. And so the bottoms, you're gonna trig substitute for x plus 1. Okay. So we could say we're gonna let x plus 1 be tangent.
No, 6 10.
Oh, 6 times tangent. Okay. So we're saying x plus 1 over 6 is tangent, or x plus 1 is 6 tangent. Okay. Do y'all agree we could do that? Take this thing right here, factor this 36 out. x plus 1 over 6 squared plus 1. Okay. So since that was the suggestion, let's continue with that and then see what happens here. We'll have this. This was tangent. Maybe I should write another step out just so we're not missing pieces. So that came from the bottom. Need that there. Want this to be tangent. So the 2x plus 1, we've got to figure out what is 2x plus 1 and what is this dx in terms of theta. Because we don't want to leave it like that.
So, plus 1 and minus 1 on the top.
Okay. Plus 1 here,
Yes.
and then minus 1 over there.
Yes.
Okay. So why are we doing that? We now have, that'll allow us to have a 2x plus 2 minus 1. So what's the benefit of having a 2x plus 2 on top?
You can rewrite it as 2 parentheses x plus 1 and then rewrite that as 2 tangent theta.
Right. Right, does everybody see that? Is that where you're going, Tree?
Yeah.
Okay. So this 2x plus 1, we have to add 1 and subtract 1 from the top. Then we have 2 times x plus 1 right there, minus 1. We know that this x plus 1 is 6 tangent. We have 6 tangent, 2 times 6 tangent theta minus 1. So let's write that here. Maybe I'll write it below. So that's 2x plus 1 in disguise. We have our tangent squared minus or plus 1 on bottom. And then we need to figure out our dx, which means we need to take the derivative of our substitution. So what would dx be?
Six secant squared of theta. E theta.
Yep. Because we've got x is equal to 6 tangent theta minus 1. So that's 6 secant squared. Theta d theta. Does that look better? Looks kind of worse. Because when we looked at this thing here, we've got two things, 2x and the 1 over a square plus 36. When we look at this thing, we have two things on top times this other thing. It's even more complicated, right? We have a 6 secant squared times our 12 tangent theta minus a 6 secant squared again, all over tangent squared plus 1.
The denominator, couldn't you rewrite it as secant squared and then cancel out with that secant squared by the e theta?
Right, right. So then we were gonna have to simplify this in terms of the identity. We get rid of this, and then we integrate a tangent and a negative 1 basically with some constants in there. So. Okay, does anyone have any questions on where we're at though? So then we're gonna address this right here as secant squared. So I'll just write it so we save space. That's secant squared data. That's dividing with the secant, or secant squared rather. Okay, so we've got our constants here. We've got our 12/36. Integral of 6 tangent. I didn't do anything with that one yet. 6 tangent minus 1 d theta. So we just took care of the 136, the 2, and the purple 6 there. So we get 1/3. Okay. Questions? Are you all okay? Alright. What is, so let's look at this in 2 ways. We've got 1/3 integral of 6 tangent, antiderivative 6 tangent, minus 1/3 antiderivative of 2. It's the antiderivative of tangent.
Why do we have the 1/3?
Because of this 12/36, this right here, and the 12.
Isn't there
Oh, we
a
can do
minus
this
one
because we have the
that
minus
would
1 over there.
distribute over?
Where?
The minus one that the 2 would distribute over, right? So that would be minus 112. 12 out.
Well, we wrote, this is 2x. Oh, yeah, so this is, let me erase that. So that, yeah, that 2 is actually attached here. So yeah, we should be careful, thanks. That was this 2x plus 2 minus 1, so this is like all together. So we should not get that one. We should just do the 6 over the 36. 6 over the 36, purple 6, 136, and leave this as 12 tangent. 12 tangent of theta minus 2. Thanks. Sorry about that. Is everything else okay other than that? I'm second guessing this. So that's what it should be. All right. Again, what's the antiderivative of tangent?
Natural log, right?
Yeah.
Natural log of secant theta plus tangent theta.
That's the derivative. That's the antiderivative of.
Oh, antiderivative. Oh, of
that's the-
secant.
yes.
Never mind.
That's the antiderivative of secant.
Is a log. Log, like the cost.
Negative.
Yes.
Yeah. Negative log. So negative natural log absolute value of cosine, or the natural log of the absolute value of secant. So either one. I'm just going to use that one because it doesn't have a negative in it. Okay. All right. We have, well, let's, I guess it doesn't matter what place we resubstitute, but we have this option was x plus 1 is, tangent of theta was x plus 1 over 6. Okay, so there's tangent of that angle. And the hypotenuse would then be what for this setup?
Square root x plus 1 squared plus 36.
Yeah, it's basically what we started with, right? This thing. All right, I think we have to pick up on Thursday with this. I suppose the other option from the 2x plus 1 over the x squared plus, or x plus 1 squared plus 36, from here, I guess we could have done a u substitution and then split that integral up. That would have also worked. But we'll pick up here on Thursday. Do you have any questions before we go? Yeah.
The 2x plus 1 and minus 1 step, what did you do there?
This step right here?
Yeah.
Well, we did that because we had the 2x plus 1 on top, and we're trying to think about, okay, well, what does 2x plus 1 look like in terms of our tangent?
Okay.
And so if we multiplied the x plus 1 by 2, right, so if we had the 2x plus 1 like that,
Yeah.
it's not as straightforward. You have to think of it as 2 times x plus 1,
Okay.
which is really 2x plus 2. So then we thought about, all right, well, how do I take 2x plus 1 and make it look like 2x plus 2?
Okay.
So we add 1 there, which means we had to subtract 1.
Okay.
See y'all.